All right, so in this video we'll have a sample problem that looks at fluid kinematics, in particular the velocity field and what we mean by a streak line. And so streak lines and path lines are something that we can actually visualize in a real system, whereas streamlines are useful for analysis. So we're going to focus here on streak lines, but know going forward that since fluid mechanics deals a lot with analyzing fluid systems in a theoretical fashion, that going forward what we'll deal with most are streamlines. And for something like this, where we can see it's going to depend on time, the flow basically changes with time, and flow changes with space as well, that well, I guess we're thinking about a particular location in space. We'll get into that as we talk about the system, but streak lines and path lines and streamlines are different for this system, but and the differences between them all are slight. They may seem like not important differences, but they actually are when we're talking about a system that does change in space and time. And just know that going forward, streamlines are what we're going to focus on. But in looking at a streak line, we'll be able to really practice what we mean by a velocity field and make some predictions out of it. Okay, so let me pull up the real problem here. So 412 is our problem, and gosh, it's a paragraph here of words that has talks about how we have radioactive steam being released from a nuclear power plant. So we can think about this as just, at one particular point in our two-dimensional field. So the point is -1, 3, where our dimensions will be miles. We have particles coming out that we want to trace. We want to keep track of them, because anywhere those go, they're radioactive, and we want to make sure that they don't come near population centers, let's say. So it might feel a bit contrived, but in its nature, it has a lot of important applications here for atmospheric flows and pollution. So the wind conditions then that carry the steam. So first of all, the release of the steam is only for the 5 hours, but then we have expected wind conditions to then use and look at to predict where the steam is going to end up going and places it's going to travel through, to make sure we warn any cities downstream that could get hit by this radioactive steam. So we're given some velocity, expected velocity data, and I summarize it better than the book did in their problem statement, which is to say, this is what I said, that we have steam being released at a particular point for 5 hours, and our goal is to draw some streak lines. But the wind conditions here I put in tabular form here. So for the first 3 hours, U and V are given as 10 and -5 miles per hour, respectively. Between 3 and 10 hours, the east velocity is 15 miles per hour, and the north velocity is 8 miles per hour. And then beyond 10 hours, the expected wind is to go 5 miles to the east and nothing to the north or south. Okay, so what makes this a little bit hard here, and we have to be careful, is that our wind conditions we can assume constant over this period, but when the steam is being released for the first 5 hours, we have a change in what the wind pattern is. Right, and so I say this is a bit contrived because we're not going to have just for the first 3 hours this is exactly what the wind is, and for the next 7 hours it's going to look exactly like this. But going through something like this on a first shot, just by, you might need computers to really simulate weather and where the wind is going to go, and it's continually changing. But even just a first shot at this to get a rough idea, just say for these first 3 hours this wind looks like this, and we have some front coming through, it could change like this. Gives you a general idea, and maybe that's all the tools you have at your disposal to send out these warnings that radioactive steam is coming. All right, so a reminder here that a streak line is a line made up of all particles that previously passed through a single point. So previously, I mean previously in time, all particles that pass through a point make up a streak line. So that's what we're dealing with here. Whereas path lines are you just follow a particular particle as it goes about its flow through time, and you make a line out of that, just one particle. This is now all particles that went through a previous point. And that's what's going to be important here, because if you make this streamline of the radioactive steam, that's the dangerous, those are the dangerous particles. We're not interested in just following one particle, because if you're going to be going, if you go through a location in space where a particle used to be, you don't really care. You just care as if you're in the way of any of these particles when they come through and hit a city, let's say. Okay, so here's our analysis. Let's going to take, we need to draw the streak lines at 3 particular instants in time, one at 3 hours, one at 10 hours, and one at 15 hours. Let's start with the 3 hours and work our way forward. So we have the initial steam being released at 0 hours. So the first bit of radioactive steam that was released has traveled for these first 3 hours from this original location of the power plant at -13 up to a location that now has changed due to the wind. So that first bit of steam traveled for 3 hours at 10 miles per hour in the x direction, and traveled for 3 hours at -5 miles per hour in the y direction, in the north-south direction. All right, and then so these are kind of the delta x, delta y, the changes in location. We add that onto the original location, we get 29 miles and -12 miles. And the steam that's released after the initial release steam now just lies on the line in between, right? So let's see if I can take my diagram and just show you the important stuff. So here, we have, here's the power plant living here at -13, and that initial steam that was released 3 hours ago is now traveled to this point. And then everything, this is also, this now looks like when these, this also represents when these particles were released in time. Right, so as you backtrack toward the nuclear power plant, that was released later and later in time in this 3 hour span. But in the end, this is our streak line at 3 hours. So some steam has traveled all the way here, and anything else in between is now lives on this line. Okay, so that one's pretty straightforward. We move on to the next one. It asks for the streak line at 10 hours. That becomes a little bit more tricky, because now the wind changes while steam is still being released for 2 hours. So from 3 to 5, steam continues to be released, but it's subjected to a new wind. And that wind now now we have a new delta x for this little period, right? So now we have an additional 2 hours traveling at 15 miles per hour in x, right? 15 miles per hour and 8. That's the conditions we're now in. And our delta y, our change in the north-south direction, we have another 2 hour time span here traveling at 8 miles per hour. This just gets us up to 5 hours, not the 10 hours that we're looking for here. But I just want to separate the time where the steam is no longer being released, and that's at 5 hours. So here we have a new delta x and delta y that are 30 miles to the east and 16 miles to the north. So therefore, at t equals 5 hours, we're going to draw another streak line that the problem statement didn't ask for. But what this streak line will make up at t equals 5 hours, at 5 hour time, is the streak line that we had for the first 3 hours, or the part that comes from A, is the whole line is translated delta x and delta y, right? So that whole line now travels 30 miles to the east, 16 miles to the north, so in a diagonal fashion. That whole line is just going to travel that way. While new steam is being released, now we can just kind of treat that the same as we did for this line. And that is to say that for these last 2 hours, the steam that was released is now, we have a streak line that goes from -13 up to a new one, which is the original location plus our new delta x's and delta y's. Okay, so let's show that graphically. I mean, I worked through the numbers there, but here is now the dashed green line is our streak line at 5 hours, right? So this streak line at 3 hours, now all of this radioactive steam has translated into this line. And we have additional steam released from 3 to 5 hours, making up this line. Okay, so you can think about this now still represents time. This was released at t equals 0, backtracking down to t equals 3, backtracking here to t equals 5 hours. Okay? Now, at t equals 10 hours, which is what we really asked here in this second part, this segmented or piecewise streak line translates another. We're not releasing any additional steam for this now 5 to 10 hours. Instead, this whole bit now translates an additional 5 hours in time at that velocity field, 15 miles per hour to the east, 8 miles per hour to the north. So our new delta x will be 75/40, and that gets added on to what we already have here. Okay, and so you'll see that here is in red. The blue is going to be, coming later here, but we see we're now translating this entire line, a delta x of 75 and a delta y of 40, such that 1,3 goes up to 74/43. 2919 now becomes 104/59. Right, so you can imagine from the 5 hour to the 10 hour period, this is the steam that's being translated up this way. All right, and then when we get to 10 hours, our wind changes again to just pure 5 miles per hour to the east. So the wind calms down a little bit and goes directly to the east at 5 miles per hour. So we're just going to get another delta x of 25 miles per hour to the east to get to our streak line at 15 hours, and we're going to get no change in the y direction. And so therefore it'll just translate directly to the east, that 25 miles. All right, so you can really, just by drawing this out, we really get a feel for how the steam was released, and that this does represent when the steam was released and how it's traveled through time after the release period was over. So it's releasing steam to here for the first 3 hours. This then translates up to here, and we get more steam being released. And then from 5 to 10 hours over the next 5 hours, that whole cloud of steam translates up to here, and then the wind changes and it translates over to here.